Heat transfer examples. In this video, we go through some examples on heat transfer mechanisms. Let's look at example 17.11 from the textbook. A styrofoam cool box has total wall and lid area of 0.8 meters squared and wall thickness 2 centimeters. It is filled with ice and water at 0 degrees centigrade. The outside temperature is 30 degrees centigrade. Find the rate of heat flow, that's the heat current, into the cool box. Second part of the question, how much ice melts in 3 hours? We know the thermal conductivity of styrofoam, and we are given the other numbers, so we plug them into the formula, and we find that the heat current is equal to 32.4 watts. Now, how much ice melts in 3 hours? In 3 hours, which is 10,800 seconds, a total amount of heat Q equals H times T flows into the box, which is absorbed by melting the ice. So Q is equal to M times LF. Here's some calorimetry. Then Q is equal to HT, we've seen that, is equal to M times LF, and we can solve for M to get 1 kilogram. Example 17.12. Two metal bars are joined together at a junction. Steel on the left with a length of 10 centimeters and copper on the right with a length of 20 centimeters. The temperature at the left of the steel bar is 100 degrees centigrade. The temperature to the right of the copper bar is 0 degrees centigrade. And the temperature at the junction is unknown. In cross-section, the bars are a square with one side 2 centimeters. The thermal conductivity of steel is 50.2 watts per meter per Kelvin and of copper 385 watts per meter per Kelvin. We are asked to find H, the heat conduction current, and the junction temperature Tj. H is constant across the bars. It flows from the left of the steel bar and through into the copper, keeping the same heat conduction current all the way through to the right-hand side. So H of the steel is equal to H of the copper. The cross-sectional area is the side squared, and that's 4 times 10 to the minus 4 meters squared. Using the formula, the heat current for steel is KATH minus TJ over the length of the steel bar, and that's equal to the heat current in the copper given by KATJ minus TC divided by the length of the copper bar. We solve for TJ, and we get 20.7 degrees centigrade. Now that we have the junction temperature, we can put it into the formula for either HST or HCU to find the heat current, which we find to be 15.9 watts. In example 17.13, the two bars are no longer joined, but are separately connected to the hotter and the colder temperature. We are then asked to find the total heat current, which is the sum of the heat current for each bar. In this case, it's easy to work out HST and HCU, and if you go through the process, you will find that the sum of the two is 97.1 watts. We look at example 17.4 from the textbook. A thin square steel plate of 10 centimeters on each side is at temperature 800 degrees centigrade and has an emissivity of 0.6. Find H. First, let's not leave the temperature in degrees centigrade. We must convert it to Kelvin. So the temperature in Kelvin is 800 plus 273, which is 1073 Kelvin. The area of the square is the side squared, but there are two sides to it, so emission occurs on both sides of the plate. So the area of the square must be multiplied by 2 to give a total area of 0.020 meters squared. Then H is equal to AE sigma TK to the fourth, which is 902 watts. Example 17.15 includes absorption as well as emission. The human body has an area, on average, of about 1.2 meters squared, and let's say a surface temperature of about 30 degrees centigrade, and an emissivity of about 1. The body is in surroundings with the TS, temperature of the surroundings, of 20 degrees centigrade. Find the net heat outflow from the body. We find the temperature in Kelvin. For the surface of the body, 30 plus 273 equals 303 Kelvin, and for the surroundings, Ts in Kelvin, 20 plus 273, which is equal to 293 Kelvin. Then we use the formula H net is equal to AE sigma times T to the fourth minus TS to the fourth, and putting in the numbers, we find a net heat outflow of 72 watts.